So next up on the alpha stage, at certain points, any of you who've worked with .NET will have had that point in your career where you look at a piece of code and you're like, my code's fine, but it doesn't work. The compiler must be broken. Now, you're wrong. You're wrong. Almost all of you are always wrong. There are very, very few people in the world who have pushed the limits of what C# can do to the extent where they have actually found things in the compiler that don't work, or the select statement in SQL Server is broken. It's my great pleasure to welcome to the stage one of those very few people. Please welcome, some of you may remember him from the days of working on in Hibernate. Today he owns and runs RavenDB, one of the best performing databases on the .NET platform. Please give it up, talking about database internals, Oren Eini.
Thank you. Thank you very much. I'm here to talk about really old topic. The topic of the conference is looking to the future, but I'm actually going back in time. And the reason I'm doing that is that I'm teaching in university and I run into so many cases where people miss the foundation. So I want to give you a guided tour into how you build a database. This has been what I've been doing for the past 15 years or so. And I built RavenDB, I built other databases before that, but there is also a really nice book that I wrote, almost 300 pages, taking it from I have a C compiler and an empty file, and all the way to I have a database. And the primary reason for this talk is one thing. People don't understand databases. You put data in, you get data out, you spin it all around, etc., etc. I'm not going to do the song. But the problem is that there is magic in the middle. And people treat it as black magic. And if you don't understand that magic, it means that you aren't able to take effective control about what's going on. So think about it from the get-go. A database is not something that you care about. A database is you put it in, you just forget about it, and you're done. You don't need to understand how it works. And then you realize down the line that, oh, I don't have an index. My system is crying because I'm doing 200 queries to the database per page load and things like that. And from a personal perspective, I find database endlessly fascinating because they're almost purely computer science. Algorithms and interactions and all sorts of stuff like that. So, by the way, in general, huge amount of research and materials and PhD on the topic. So almost no excuse to not to learn about them, at least from my perspective. I somewhat got into the topic almost by accident. I got into the topic because I hated working with databases. I didn't understand them. And then I did understand them, and then I built one, and then I realized that the problem was that they are pure misunderstood beasts. Probably the most interesting thing is that as a database author, you're so limited by what you have, which sounds really ridiculous. We have things like RavenDB, SQL Server, Postgres, SQL. Why is it so limited? And then you realize that there is a huge amount of work that you have to do just in order to do the simplest thing. And it has an impact across the entire ecosystem. So let's talk about this. What do you need from a database? Number one, transactions. ACID transactions, which means that operations are atomic, durable, the whole thing. There was a phase in 2005 to 2015, more or less, where people thought that you can have database without transactions. To my knowledge, there is almost no database today without transactions. This is a mandatory feature. As a database engine, you have to address queries. And the simplest possible query is get me something by ID. This is how Redis works, by the way. And conceptually, this is very simple and makes things a lot easier for the implementer. It put a huge constraint on the people using the database. So we moved to actually having more efficient queries, or more, not more efficient, but more powerful queries. But it means that the database has to do a lot more work. How does it do that? And dear God, the amount of SQL that people write to make the database do something is absolutely scary. Anyone here ever saw a query that went over more than 300 lines? Yeah. Anyone had to debug an issue there? Anyone went out and built a database all on its own so he wouldn't have to do that? Yeah, it was that bad. Anyway, a lot of databases today also deal with distributed computing, so we will not touch on that at all. We are only going to talk about a single node databases at this point. And most importantly, from the perspective of the database, we deal with disk, I/O, and CPU. Sorry, disk, memory, and CPU, but we don't reflect that to the user. We give them some model in which they operate on. So let's look at what is involved. First of all, for databases, N is large. No one cares about your database if you have a 10,000 or 100,000 records. It used to be the case that a 100 megabyte file dataset was huge. Now it's a JSON file. Maybe you zip it, maybe you don't. No one cares. But it's interesting because when you start getting a large N, where N is hundreds of thousands, millions, tens, billions, etc., then those numbers, the complexities start making a real pain for your implementation and details. So how do you make this work? So the first thing, we're going to focus on how you make transactions work and then queries. Why do we care about transactions? Why do they matter? Very simple reason. What happens if you don't have transactions? Then the level of guarantees that you can provide to your user is minimal. Give me your money. I might have done something for you, or I might have not. Or I might have done something for you, but not gotten the money. I don't know which one is worse. And then you are faced with requirements from the users. I want to know what happened. So if you don't have transactions, you have to go and build them in some manner. MongoDB at one point had a 30-page document explaining to you how you could implement transactions on top of a non-transactional store, MongoDB at the time. And I remember looking at it saying, I found 3 different bugs in the sample code that I provided, and no way someone who is not familiar with databases can implement that correctly. I had the pleasure and pain of implementing transaction store multiple times. It is not trivial. So let's start talking about the very first consideration in the database. What is the communication model that you have? Who cares? What does it mean, communication model? So if we're used to SQL, we have the model of a phone call. Hi, I want to know how many users are with red shirts in the building. And then I get a result. And then it says, okay, take the first 3 users and change their shirt color to blue or something like that. And then I keep on giving instruction and queries while I'm on the phone with the database. Eventually, I commit a transaction and shut down. This is how SQL works at a very fundamental level. Conversely, you may be able to send the whole batch of operations to the server as a single unit. And why does it matter? Consider how it looks from the perspective of the database. If you use the messaging system, where you send a bulk of messages or commands or queries or whatever in one shot, versus you're on the phone. I'm a concurrent system. If you send me a bunch of messages, if you send me a fax with detailed instructions, I can process them as I go. If you hold me on the phone, and I'm sending a query and you think and you send me a command back, in order to get concurrency, I actually have to maintain multiple concurrent transactions at the same time, manage lock-in, manage operations, all sorts of stuff like that. It turns out that the communication model for the database has a huge impact on the overall design. By the way, if at all possible, go with the messaging model. Because the messaging model is you get an email with all of the instructions to do, and then you just say yes or not. It gives the database a lot more freedom. Consider what happens if I get 2 emails at the same time. I can process each one of them individually, or I can look and see between those 2 batches of commands that I have to do, what is the optimal order to do that. On the other hand, if I have two concurrent phone conversations, I have to follow them serially without being able to decide what is the optimal path. This is leaving aside the lock-in and consideration around that. So there are two types of databases. Ones that put stuff in memory. We don't care about them. And stuff that writes to the disk. And writing to the disk is fraught with peril. Why is that? Because disk sucks. And it sucks so much. This is really annoying. Here's a big issue. I'm writing to the disk, and the simplest database possible is a CSV like we have right now. And let's assume this CSV has 10,000 records. And I want to update this value. What is it going to take? There is literally no way of doing that. Because notice that I'm updating the email field to be bigger than it once was. At one point in time, there used to be fixed size fields, specifically for that purpose. So you would be able to update a record in place. But a CSV like that, I would have to overwrite the line, and I have to move and shift all of the bytes following this line. If I have a large file, this is impossible to do. I can have a log file. A log file is a very simple database. I append in the end. It's sorted by time. If I want to do queries, I either do a ON operation and scan the whole thing, or I can do a binary search by time alone. Pretty easy. CSV, already spoke about it, but still, notice that I'm limited by the facilities provided to me by the hardware, by the API that I have from the operating system. So let's talk about the API. This is at the lowest level of writing to the disk. This is the write to a file at a particular position. Notice that I don't have a way of saying, oh, shift everything else forward. There are actual APIs for that, by the way. If you build a production system on that, may God have mercy on your soul. Don't do stuff like that. Absolutely not. By the way, in terms of databases and the sort of thing that they are acceptable, you go conservative. If an API hasn't been around for 30 or 40 years, it's inexcusable to use it because it would break in all sorts of interesting ways. So I cannot write to disk whenever I want. So I have to organize the data on disk in some manner. And the way that we typically do that is to use the concept of pages. And in order to understand that, go and think about a file folder where you have all of those pages. And you can take a page and you want to modify it. You can modify some of those details. But at some point, you write in an append. So at some point, you need to overwrite something. So you take a new page, copy everything to that page, write whatever you want, and then put the new page where the old page used to be. In terms of actual file data, we divide the file into 4 or 8 or something kilobyte increments. The hardware always operates at 4 kilobyte increments, so that is what we'd usually use. And overwrite that in one shot. So read 4 kilobytes from the disk, modify it, and save it back. Which means that any value that we have has to fit into 4 kilobytes or 4 kilobyte increments. It also means that when we write data, we have to consider how do we organize that. Going back to this tip, how do I organize records in pages? Because I now want to be able to modify a page, and it has to make sense. So we use something like that. We have a page. Imagine this is a 4 kilobyte or 8 kilobyte page. And what we're going to do is just store the records there in sort order for that particular page. So we have all of those names and everything is good. There's a problem. If I had a database that only needed to store up to 4 kilobytes, I had a very simple life indeed. But I need to store more than that. So what do I do at this point? Look, I need to install HANA to this thing. So what I'm going to do, I'm going to split the page. So here is the old page, and I created a new page in here just with HANA. But I have to have some order. So I have a root page. And the root page says everything that is bigger than Abel should go to the top one. Everything that is bigger than HANA should go to the lower one. And now I have structure. This method is called a B+Tree. This is one of the more fundamental data types for databases. But notice that there is a problem still. I added HANA at the end of the page. What would happen if I had to insert Ben? If I'm looking at the sort order, I have to split the page in the middle. So look what happened now. What happened now is that I split the page at Derek, so Abel and Derek, and if I now want to put Ben, I put it in the top. This is again a page split. And the key here is whatever we added at the end of the page or in the middle of the page. Why do we care? I mean, that's a detail, right? It turns out that this has a huge impact on overall performance. What you see here is a multi-level B-tree. It holds the same data. But the difference here is that at the bottom one, you can see that it was inserted in a sorted fashion, which means that every time that we had to split a page, we could just create a new page and not move data around, which means that the height of the tree is shorter than the previous one. And if you think about that, a page is 4 kilobytes. So I start from the root page, and let's go back here. I start from the root page, and I want to find Frank. So I'm going here, I read this page, and then I'm saying, okay, I need to go to find Frank, so I need to follow this link, and I find Frank. But it means that every level of the tree means another I/O operation. So the deeper the tree, the slower things become. So it turns out that the sort order that you have has a huge impact. The insert order into the database has a huge impact on the overall performance. If you ever had used sequential GUIDs in SQL Server, or were told, oh, you should use an integer key instead of a string key, it is for that particular reason. Because if you insert data in a sequential manner, it is far more efficient. Now, just to give you some ideas about how all this is, there is a really big paper from 1979, and that's 43 years ago. And at that time, B-trees were considered to be ubiquitous. And if you think about it, the moment that you start thinking about how you organize data on disk, you pretty much come up with a B-tree. There's a huge number of variants, and they have some aspects of this is better, this is worse for different considerations, but B-trees are at the heart of many file systems, many databases, etc. It makes very little sense to organize things otherwise. There are databases that use different methods. I will show that later on. So here's a question. What do you put in a B-tree? A B-tree is a sorted data structure. And at the leaf of the tree, you can put the record itself. And that's great. So you walk the tree, you find the final value, and you get Abel. And when you get Abel, this is the record, and then you get all of the name, the phone, whatever we have for that person. There is a problem with that approach because I can only fit so much data into a single page. So if I put the value of the data inside of the B-tree, it means that by necessity it's going to be deeper. On the other hand, I may use a reference model where that data, the actual data for the record, is stored somewhere on the file, but the B-tree just stored the reference to that, which means that the B-tree would usually be shorter, would be shallower, sorry. what happens if I have a larger value? I have a record that is 16, 15, no, let's say that I have a record that is 21 kilobyte in size. Why? Because someone decided to write a pretty long rant about why database and really hate disks. And the answer to that is that we cannot store that in a page. So we store it in something called an overflow value. We allocate the number of pages that we need to store that value and just store a reference for that. And you will see that coming up again and again, the notion that we add additional indirection. Now, some key aspects here, and I use the key intentionally. A B+Tree is sorted, but sorted by what? Can you tell me? What does it mean that a B+Tree is sorted? If I'm storing the data inside the database, and I'm using a primary key, the primary key may be an email, it may be a compound, last name and first name, something like that. Whatever the key is for that record is the sort key for the B+Tree. Which means that if I want to do a lookup by a key, it's very easy. Run through the sorted value, get the value, or log in. If I want to get a prefix, give me all of the Smiths that I have in the phone book. Well, the sort key is last name, first name. Very easy to do that. Give me all of the users from 100 to 200. The user ID is sorted. So running a prefix search, running a search on the minimum value and then scanning from there is trivial. All of those are really, really cheap operations. But you know what? I have a B+Tree that represents users. And the users are actually sorted by the user ID. I want to search by an email. How do you do that? How can I search by email? Sorry? Full scan. Go and scan the entire thing. It works. I mean, as long as you have low amount of data and low number of users and you don't care about performance at all. So now, and think about it. This is the root cause. I have a full scan of the record. How can I avoid that? How do you solve anything with computer science? Add another level of indirection. Do a B+Tree. You have one B+Tree which is sorted by the user ID. Have another B+Tree where the key is the email and the value is the record, but you don't keep the record twice. What you do instead is you have two options. And the first option is the secondary index, which is the secondary B+Tree, is referenced, the sort key is the email, and the value of the B+Tree is the user ID. So what do I need to do then? I need to first do a lookup on the secondary index, then do a lookup on the primary index, and then I get to the actual value. Conversely, I may choose to do what we have in the top picture, where the secondary index, the email index, points to the same location on the disk as the primary index. It doesn't sound like it's a major change, right? Well, there is a blog post from Uber Engineering from 2016, I think, that talks in detail about this particular design decision, where Postgres does the secondary to the primary index, and MySQL uses both primary and secondary index points to the actual record location on disk. And that can have a major impact on performance. Let me give you a simple example. I want to search for all of the people who live in Vilnius. Let's talk about what is the cost of doing that. I have an index of users by city. If I'm storing, say if the secondary index store a pointer directly to the record location, what do I have to do? Go to all of the users all of the records for Vilnius in the index and start pulling the records. This is a O-log-n search on the secondary index, and now I'm done. Because I'm assuming that pulling the record is a O1 operation. in the case that the secondary index holds the primary key value, I would have to go to the index, and then for each one of the user records, I have to do a search in the primary index. So this is a log n operation on the secondary index, and n times log n on the primary index. And that can have a huge impact on your overall performance. Now, let's talk about ACID, and not the kind of thing that you take, but the guarantees that you get from the database. Atomic, consistent, isolated, durable. They suck. They suck so much because I have to implement them. And it wouldn't matter that much if the entire ecosystem around storing data persistently was so horribly broken. I'm not bitter at all, by the way. Let's talk about this. I/O sucks. I/O sucks because it is a whole big lie. It's slow. It's slow to the point where you never actually write to the disk. I want to write to the disk. So what do? Open file, write, close. I'm done. Not really. I write to a user mode buffer. And then at some point, I'm flashing to the OS buffer, which at some point goes down to the file system buffer. There is a driver buffer. There is a physical buffer on the disk. Sometimes there is network in the middle, and no point did anyone actually thought about how do I make it actually work properly. This is a kludge on top of a kludge, and no one actually wanted to do that. And you cannot fix this at this point. So it used to be the case that you had an NVMe drive. A HDD drive, hard disks. And they span, and they had revolution per minute of, wow, I have 10,000 revolutions per minute, which means that I can do 150 revolutions per second, which is the maximum amount of random writes that I could possibly do under optimal conditions. And you cannot do that. It's the user wouldn't be sitting there. Every click is going to take multiple seconds to handle. So you have all of these bufferings. And now we have NVMe drives, which are supposed to be so much faster, but they're still so slow compared to everything else that we have to introduce all of these bufferings. And if you make a write and you save a Word document, and then you pull the plug, there is no guarantee that the file will be saved. Because you write, and at some future point in time, will it actually go to the disk? On Linux, for example, a persistent write to a file is typically made persistent within 30 seconds to 5 minutes. That sucks. But you know, I write code. I can fix that. I want to make a write and make it persistent. So I wrote some code. Open the file, write, close. I'm checking the error codes. I'm good. Do you see the horrible mess that I have here? Here is a hint. Do you see this, the close method, the close function? Here's a hint. It has a return value. Close can fail. Now, excuse me. What the hell am I supposed to do at this point? I close the file. I failed to close the file. What am I supposed to do? But let's leave that aside. Let's say that I handle, in some fashion, I have no idea how to do that, that failing to close the file. I haven't made the data persistent. So if someone pulls the plug, if there is a concurrency or something like that, I have to worry about that. So I fixed that. I wrote an Fsync. Fsync is an API that forces the system to write the data to disk. Am I okay now? Okay. It does not work on Mac. In general, by the way, do not run databases on Mac at all. At all. Fsync, there used to be a huge kerfuffle about Fsync in Linux in 2008, where Firefox called Fsync 30 times a second. And it would mean that the entire system grind into a halt because it would keep flashing the disk, and blocking I/O, and a whole bunch of other stuff like that. And in response to that, on Linux, Firefox stopped calling Fsync all the time. In response to that, and to other pressures, Apple decided that Fsync is not important and did not implement that. You can still call it, it does nothing. There is an fcontrol full sync command in Apple, which does not do what you think it does. It sort of tries sometimes to do the right thing, but it doesn't do that. You cannot actually write a proper database on a Macintosh, or an Apple OS, or all of those sort of things. But leaving that aside, let's assume that I'm running on a reasonable file system, on a reasonable platform, that you actually get guarantees. What's the problem with this code? Sorry? Fsync can fail. Fsync gate. A data corruption in Postgres that was narrowed down to Fsync can fail. And the way that it works goes something like this. I'm writing to a file, and then I'm calling Fsync on that file, and it fails for whatever reason. What would happen? Well, from the operating system point of view, I tried writing it to disk. It did not write to the disk. Okay, I return an error to the system. And I'm marking all of that data in memory as if it was successfully written to the file. There are good reasons why it does that. But from the perspective of a database developer, it means that I have an inconsistent state between the database in memory and the database on file, and I think that the term is hilarity and queues at this point. So there is a huge number of content around that. Dan Lu wrote about this a lot, and those are fascinating topics. Also, there was a study on whatever application can fail from an Fsync. Fsync failure. The answer is no. The only way to recover from an Fsync failure is if you're a database and you apply recovery. I will touch on that in a bit. In short, here are the steps that you have to do in order to successfully write to a file. You have to write to the file, Fsync the file, close the file, open the parent directory, Fsync that recursively. Why is that? Because even if you successfully Fsync the file, if you modify the file size, the metadata file is recorded in the parent directory. Yay! Subtle bugs that you never see. Okay, so this code that we have right here, this is about successfully writing to the file. But what happens if there was an error? I still need to write. I still need to be able to operate. So we cannot modify data in place, because if I modify the data in place and I fail to write, I still have to recover somewhere. So I have to have some secondary location where I'm handling that. There are two typical ways of doing that. One of them is the write-ahead log. I'm going to make a change. So I'm either writing what used to be there or what will be there in the future to a secondary location, make the commit, actually persist the value to disk using Fsync or some other stuff, and then actually go ahead and modify the file. The other side is that I'm never actually writing to the same location. I have to always write at the end of the file. This has the interesting problem that at some point I run out of disk space. So I have to do a compaction. And if you have to do a compaction, that means that physically you need at least twice as much free disk space. So if you have a 100 gigabyte file, you may very well need a disk that has 200 gigabytes to operate properly. It's more complicated, so you don't actually need it at this point, but it's a serious consideration that you have to consider. So with the write-ahead log, we get some really interesting behaviors. I can write to the end of the file in a sequential manner, which is great for performance. I can do that in a durable fashion. You can open a file in a mode that tells the file system and the operating system write all the way to the disk and don't wait up. And do wait up. Don't buffer. I need to have the data hit the disk, and there is something called force unit access flag on SCSI that you can tell to the disk. I need you to confirm this right only after this has actually been made persistent. And this actually is far better than using Fsync, because Fsync means I wrote to the buffers, and now I need to flush all of the buffers in the middle. With durable mode, which is O-direct or file flag write-through in Linux and Windows respectively, you have the ability to say, just skip all of the buffering and go to the end, which tends to be far better because you're not flushing large amount of memory. So we are writing to the file, to the log file. And there are two options. There is the redo log, which I'm saying, okay, I'm going to write to a page. Let's take the page content before the operation and write them to the log. And conversely, let's write the modified page to the log. So either it's about how you do recovery. I'm not going to get into that. But basically, I'm saving enough information in the log to reconstruct any transaction, reconstruct the state that I have. By the way, the reason that you might want to do a redo log is about if you have the conversation model. Because I'm about to have a really long conversation with you and you're going to modify a page multiple times. I don't want to write it each time to the disk. So what I'm going to do, I'm going to write the original state to the log file and then modify that in place with log and associated data around that. So this is how you write the log file with O-direct and O-sync. There are lots of limits on that, but conceptually, the database commit is completed once the log write is done. Now, here is a very subtle issue. It is perfectly fine that you say, oh, I want to write a megabyte to the log file, and you crash in the middle. What was written to the log file? Who knows? It's a wonderful surprise for you when you start up. So you have to figure that out because there are multiple options. Either you failed midway through, but the write was successful and persistent. So that transaction considered to be committed. Or there is some partial write or something like that. So you have to be aware that when you read from the log file, you have to somehow validate that this is okay. Checksum or something like that and things like that. Really interesting is that a log file is something that you hopefully never read because it's only used in recovery. So you have to consider how do I manage that. And something that you absolutely want to avoid is slowly incrementing the size of the file, of the log file, because each time you have to do multiple, to update the file and file metadata. So you have to pre-allocate some data up front. Here is an interesting problem. What's the cost of replaying the log? I start up the database, I start reading from the log file. And what do I now need to do? I need to go and update all of the data that I have in the log files in the data file. What happens if I'm running on an Azure system with slow I/O? Well, welcome to 2 hours where the database is down because it's replaying transactions. True story, by the way. And you know what the admin did at that point? They restarted the database, which restarted the recovery process. So you have to consider a lot of aspects on that. For example, what we currently do on recovery, we read from the log file, and we write non-durably to the data file. Why do we do that non-durably? Because we don't actually care. Because if we restart at some point, we have a failure, we read from the log file again. So that speeds up this particular scenario from 2 hours to about 2 minutes. Log file is slow, it's still a file. So you have a lot of playing around with that. One of the options is, remember that I told you that you want to have the messaging model, that you have multiple things that come in all at once and you can process them. One of the reasons to do that is so you aggregate multiple concurrent transactions into a single write to the log file. Consider the difference between taking a car, 3 people taking 3 separate cars to go to a bar and one person going there. It's a totally different cost model. Another option is something called early lock release. You have, the first option is you have serial commits. Transaction, 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 transaction. The second option, you have a transaction and a commit, and while we are waiting for the commit to complete, this is a slow I/O model, I can start to speculatively execute the next transaction. So I have I/O and computation running at the same time, and that can have a huge impact on performance. I want to touch very briefly on concurrency and how it's working. There is something called MVCC, multi-versioning concurrency control. And the idea here is that you somehow need to support concurrent reads and while you're making writes to the database. One of the best ways, I think, to do that is to consider the ways that you're processing with pages. And what's the idea? Here, all of the pages and the data in them. And whenever I need to make a modification, I'm not making the modification in place. Instead, I'm copying the file, and you can see that we have file number 4, page number 4, and instead of being Ken's there, it's Emily. And now I have a different file, a different page for page number 4. And I have something called a page translation table. So when I have when I do a lookup, give me page number 4, instead of going to the page in the file, I'm going to go to the page in the sketch. And when I commit, I publish the page translation table. So now all new transactions are going to know that, hey, I'm going to go to page 4 from the sketch, and the other pages would be read from the file. And at some point, all of the old transactions have completed, and then I can copy the value from the sketch to the actual data file. And if you think about that, it's a really elegant mechanism where all transactions have a frozen state. They have a snapshot of the database at the time of the transaction, and it doesn't take a lot of complexity from your perspective. Postgres has a similar MVCC model, but it is a lot more complicated because they store the from transaction to transaction values on a per row level, which means that they really care about the size of the from and to field, and they have a 2 or 4 billion limit to the number of transactions that you can have at any given point in time, and a whole bunch of other stuff like that. With something like that, where you switch out the whole page, it's a very different concept. But something like that requires that you will be able to replace the whole page and won't have competing transactions trying to modify the same page at the same time. So you have the communication model of the database impacts the way that you write to the disk, the concurrency strategy, and all sorts of stuff like that. And when you can write to the data file when no one is looking, and that's it. The data file itself, you need to call Fsync on that. And that's something that you want to schedule and try to figure out how you can manage the I on that. Once you call Fsync on the file, you can discard the log file, reuse it, something like that, and etc. So writing to the log file is very expensive. All I/O is very expensive, so we do a lot of playing around with that. Batch writes is one of them. But there is another aspect. Most of the time when I modify a record, I don't modify the whole page. I modify just one item, and typically just parts of the item. So what I'm going to do a diff. Here's the old version, here's the new version. Let's write to the log file just the changes. And then let's take those changes and compress them further. We burn CPU cycles to reduce how much we write to the disk. And in most cases, that is a very good opportunity, very good trade-off to do. When we are reading, from the file system, but we follow the shape of the B+Tree. And in many cases, we can say, hey, I know that I'm going to follow down. Let's ask the operating system to schedule the I/O for those particular locations before I get to the point where I'm doing that. And we talk about this. Something that is really important. The communication model impacts how I manage transaction internally. if at all possible, using a single writer model is far preferred, which sounds ridiculous. Why do I want to have a single writer instead of multiple threads? Obviously, multiple threads are going to be faster. Well, the answer is that databases spend 40% of their time just managing locks. If you can avoid that, you can save a lot of performance and have a drastically simplified model of how it works. It's a huge complication because there is no separation of concerns. And the network model, the messaging model that you use has an impact on how you write things to the disk and how you manage transactions. And all of that has to be considered very carefully. It's a lot of fun and has huge amount of excitement in it. I want to mention a couple of other options that we have for managing databases. One of them is called the bitcast model. And the bitcast model basically means I'm writing to a file, but I'm keeping the list of IDs and the keys that I have to searches in memory, just holding the position to the file. And that can be a very simple mechanism as long as just the keys that you have fits in memory. I think that Biscuits did that. I think that Couchbase is still currently doing that. But then you have serious issues. What happens if the metadata that I have is bigger than memory? And then there is a drastic cliff in terms of performance. There's also the log structure merge system for something like Cassandra or RocksDB, and I don't think that I have enough time, so if you have any questions about it, come to me later. And do you have any questions? Thank you very much.
Thanks, Oren. All right, folks, we have a break for lunch. Go out, enjoy yourselves, eat, get some fresh air. We'll see you back after lunch. Take it easy.